So my name is Chuck Wolber. I introduced myself earlier. I'm going to talk to you about using LLVM to perform code coverage on the Linux kernel. First, I'm going to start a little bit with where the motivation is. If you haven't seen this paper, it was written by a colleague of mine, Steve VanderLeest. I was a reviewer on the paper. What this does is sort of lays out the justification, the reverse engineering justification for, says how to do it ultimately, for one of the highest levels of criticality required in all safety industries. So that'd be commercial aerospace. The idea is there are a lot of techniques like we need the open source code. Open source could use the rigor, but no one's willing to accept the time and energy required to apply that rigor. And so we're working on techniques to sort of meet things in the middle to increase reliability. Everybody wins. So if you haven't read this paper, it's actually pretty interesting. Definitely recommend you reading it. What I'm going to talk about to you today is an element of that paper. This is a collaboration with the University of Illinois Urbana-Champaign. Wentao Zhang is a PhD student. He did most of the work on this. So my role was testing, helping him shepherd stuff into the kernel community. A lot of back and forth, helped him a little bit develop the patches, and of course I'm presenting and I've had a lot of fun with it myself. This paper has been accepted for publication in the Digital Aviation Software Conference 2025. So if you go to that conference, you'll see this one here. So let's also talk about some additional background. Wentao presented on this topic, this is before the paper was accepted and finished, at Linux Plumbers Conference. It's the Making Linux Fly. You can see the presentation material and a video on it. Definitely recommend it. He goes into some deep technical depth about instrumentation, code coverage instrumentation, so definitely check that out. And then Andrew Oppelt, who's also working on this team, presented at Embedded Open Source Summit in 2024, similarly on other elements of this talk. So I am more practically focused on why we're using LLVM versus GCov. So I'll show you technical reasons why actually LLVM is a better choice for code coverage. And then also how to use this. Actually I have a proposal to hopefully solve one of Tim's problems, but I want to hear your feedback as well. So I'll air it out there. I'm not afraid to be wrong. So let's see. So why does this matter? There is what's called, there's a difference between verification and validation, right? Validation is, did it do what you want it to do? And you can't code that. But verification, actually we can. We can lock that into a 3-step cycle. You need requirements. Requirements inform your test. Coverage tells you, are you hitting all the code? You got to have all three. So you tie all those things together. So there's an asterisk near requirements. Working with Kate, we have been doing a lot of work. It's a whole nother presentation. I did it on Monday. We were also at Linux Plumbers Conference talking about this. We are creating a template also to tie together requirements and code in a traceable fashion, detecting change, all that kind of stuff. So I put a link to that. You can check out that presentation there. And we could use your help too, if you want to help us with that. We've got a lot of work to do on that. Test, of course, we've been talking about that this whole time. And I'm going to talk to you about coverage. So this is a really important part of completing the verification cycle, which everybody needs. This is definitely going to improve the code quality of the Linux kernel when you complete the verification cycle. Remember, verification is not validation, okay? And it's also a significant step towards using Linux in the highest degree of safety criticality. In other words, if it works for commercial aviation, you can put it anywhere. That's the highest degree of rigor generally required of any industry. Okay. Let's talk about some coverage terminology. If you already know all this, you can go to sleep. This is some example code. There are 2 conditions in this example code, x greater than 0, y greater than 0. We call those conditions. A decision compounds those together. So this is what we mean by decisions. So there's conditions and there's decisions. And obviously you can have arbitrary size, okay? So there are generally 4-ish, 5-ish different types of coverage. Statement coverage, we should know. That's just, did you hit the line of code? Then you get into having to follow where the branching is. You've got decision coverage. That's true and false decision outcome. You've got branch coverage, which is the same as decision coverage if your language short circuits. Is there any language that doesn't short circuit logic? I assume there probably somebody has a language somewhere that doesn't short circuit. Does it really? It doesn't short circuit? Wow, okay, there you go. So in Visual Basic, branch and decision coverage are different. But in every sane language, can I say that? Okay, and then condition decision coverage, this is where you measure true false of each decision for all possible conditions. And that is an intractable problem. So no one does condition decision coverage. Once you get to like 256, right, you're solving SHA-256 ultimately. It's not practical. You can't do that. So we've invented something called modified condition decision coverage. There are two types. The easiest way to think of modified condition decision coverage is pick any condition, change it from true to false, and independently just changing that condition, it must change the outcome. If I change it true and false and the outcome doesn't change, I have not adequately tested that condition. Masking means I really don't care what happens to all the other conditions. So you can optimize on your test cases and say, I can prove that this condition changes back and forth and the result changes. The code happens to be changing other conditions as well. Unique cause means all other conditions must remain constant, only changing one condition, and the outcome has to change as a result, as a function of that. The FAA will accept masking MCDC, but we're shooting for the gold standard, which is unique cause. That gives you a better result. Okay, so let's look at what unique cause, this is an example of unique cause, MCDC unique cause. Example code, there are three conditions, okay, one decision. There are two test cases I ran here, test 1, test 2. Test 1 ran through the code 3 times, so conditions were 0, 1, 1 the first time through and so on and so forth, okay? We have 100% coverage on test 1. Test 2, we only got 1 out of 3. So we map these things together, so condition 1 is proven by the test that ran through all true, and then the first one is false. So you can see the output was independently triggered just by toggling the first one, so on and so forth, okay? That's unique cause. Okay, typical code coverage workflow. You instrument your code, it's just a couple of compiler arguments, and then you run your code. What's left behind is a profile, and you can do some post-processing on it. You really don't have to do much to get this to work, okay? It's designed to run in an existing operating system. This is what the instrumentation looks like, okay? It's just, the compiler adds the instrumentation for you, and then it's got its own linker script where it updates the sections. So when your code runs, it's a very lightweight way of testing your code, not printf statements, not ftrace or anything like that. It's a very lightweight way because it's updating code in a different section, data in a different section in your linker, in your object file, okay? These counters update as you run through the code, and then you can post-process it and you can analyze your code coverage results, okay? This is pretty standard. But it's not the Linux kernel. In user space, instrumentation can make assumptions. You have file I/O, or however you're going to gather your results, and the compiler manages your linker script. Obviously, the Linux kernel, there's no file system for you to write to, right? And the Linux kernel has its own linker script, so you have to put all that stuff in there. So let's start with LLVM. We'll get to how we did it here in a bit. MCDC was added to LLVM in the 18.1 release. Definitely recommend you check it out. There were some presentations on it. I think it was a Texas Instruments engineer who did it, and he just said he did it, I think he said he did it for fun. It was a fun thing to do. It was really cool. It worked really well. It only supports C and C++. Rust and assembly language, if you want to do code coverage right now, those require object code coverage, which means you're having to do code coverage in your binary. That's a whole different thing. Originally, it only supported decisions with 2 to 6 conditions. You can imagine, right? This is a satisfiability problem. It's dynamic programming. Go back to your dynamic programming problem. Now they can do, right, 2 to the 15th conditions. But it's not really practical because once you hit 46 conditions, you actually you exceed the kernel size limit, so you can't do that. Also, one of the other limitations that they're working on is if you have a nested condition, so you have a function with its hiding conditions, it'll print a warning right now. So when you build with our patches, you'll get a warning when you have nested conditions. There is a patch LLVM team is working on to resolve this. But right now, that will produce a warning when you're compiling. Also, it'll produce a warning if you have more than 46 conditions and you limit it to 46 conditions, and there's one place in the kernel that has more than 46 conditions. Anybody know what that is? It's the logic for CPU ID. I don't know why it's that complicated. Yeah. So, yeah. And then there's, of course, intentional exclusion. The no inster is really important for hot paths. So that's no instrument function attribute. A lot of places. And actually, that's where we found some bugs, and we'll talk about that as well. All right. So you may ask, well, what about kcov and gcov, right? Because kcov and gcov are already in the kernel, so why are we recreating the wheel? This is silly. Just use what we have, right? Well, kcov was really not meant for that kind of coverage. Okay, this is a quote from the kcov document. I pulled it out directly. Right, okay, that may be the case, but what about gcov, right? It's built into the kernel, it's already there, and lo and behold, gcov actually supports MCDC. So what's the problem here? Let's go back to our compiler 101 to explain what the problem is. You have to move this out of the way. Okay. Scanner, parser, tokenize your code, you have an abstract syntax tree, you decorate it, go on, you code generator, you got your target code, okay? Oh, there we go. This is how LLVM does it. When you're instrumenting for code coverage, same thing, tokenize, abstract syntax tree. Instrumentation is applied at the abstract syntax tree level. Pay attention to the semantic density. Semantic density is about the same at the abstract syntax tree level as it is with the code. Instrumentation is lowered along with the code itself. Let's look at GCC. GCC, they have several intermediate representations, okay? They were designed, GCC was designed at a time when people wanted fast compilation. So there's tons and tons of optimizations in here, plus they are trying to satisfy every possible language need. So there are several intermediate representations. Instrumentation is applied at a much lower semantic level. So you already have semantic lowering from your language implementation, then instrumentation is applied, later on optimizations are applied. Since you have disjoint semantic levels, when you apply instrumentation, you actually get Byzantine results with optimization turned on. So if you want accurate coverage results with gcov, you have to compile without optimization. LLVM does not have that problem. So I have evidence here. It's in the presentation. You can copy this out and prove it to yourself. So here's a code example. It's got 4 conditions, setter, exercises all of them. This is an eye chart. I put it here so you guys can copy, paste, reproduce it, and see the same results as I did. So I'm gonna zip past this. And I'm sure there's something ugly in here I'm doing in here, so I apologize for that, but it gets the job done. So this is an example of the output. I just tried to do it in aggregate. The gcov, with optimization turned on, it's 49 lines. With it turned off, 56 lines. Covering the same code. I don't know why that would be different. That seems silly to me. And then I do a diff between them. There's 91 lines of diff when I diff. All I've changed is the optimization level when I compile compile it with GCC. Come on, guys, really? So LLVM doesn't matter optimization level. I get this. It's the exact same code coverage output no matter what. You never lose information. Let's see. This is an example of what you're losing out on. So because the optimization happens at, different semantic levels, you actually, it won't even register some branches that were or were not taken. So you actually don't have an accurate result of where your code coverage is. By the way, the Linux kernel is meant to be compiled with O2, okay? And I'll go into some of the reasons why that. This is, I'm sorry, it's a little bit of an eye chart, but this is what the LLVM cov output looks like. It's also kind of nicer looking. I know you can use lcov to make the gcov output cleaner, and there's Python libraries and all that. So I don't want to bag on gcov for their really difficult to read output, but it's kind of cool the LLVM cov cut out the middleman, and they have an incredibly readable output directly from processing. So you can already tell here that I have 50% coverage, MCDC coverage on this. You got branch, and of course you got your statement coverage entries there. Okay, let's talk about the patches. So many thanks to Google and Sammy Tollivan, who had originally written patches to use LLVM to do profile-guided optimizations. Those were not accepted within the kernel, and I think they abandoned them. But Wentao was able to find them and refactor them. So here's a link to the GitHub repository with the patches in them, so you guys can try them out yourself. Plenty of documentation in there. It should be pretty turnkey to give it a try. They have not been updated. They're for the 6.12.1 kernel. They have not been updated. I'll go into why we're not, but we've submitted them, to the kernel mailing list, 2 versions of them. There are 5 patches. I was stunned at how, ultimately in the end, how simple this actually turned out to be. All you had to do was update the linker script and then add sysfs modifications to actually store the data that the instrumentation. So you just had to map the same data in the same sections, and it just worked. So this is surprisingly easy, which means it's a free throw for ARM. It works on ARM, Intel. This is not like a special architecture-specific thing. And then, of course, the rest were adding a maintainers file, adding the kconfig options, those kinds of things. So the patches are surprisingly simple, but it was a hard problem to tackle. It took us a while to get here. Testing. It's been tested to work on Intel and ARM architectures. I did not do the ARM testing. Wintao did that. He claims it worked just fine. I did mostly on Intel because that's what I had. That's the hardware I had at the time. It exposed LLVM and kernel bugs. So patches are currently held up because fixing some exposed bugs. So the easy ones, so the Linux kernel is, like I said, it's designed to be compiled with O2, which means if you turn a feature off, when you're compiling, you still need that symbol in your object file, even though it's turned off. Optimization removes it. So there's like a stub. You'll see it's like foo and then an open and closed squiggly bracket with no code in there, right? And because there's no code in there, the optimizer just removes that symbol in the end. But when you instrument the code, that symbol never gets removed. So when you have a stub that was written a long time ago, and later someone comes along and says, well, that feature needs to be on the hot path, so we need a no instrument for it, but you forget to update the stub. Now when you instrument the code, obj_tool runs, and it gives a whole bunch of warnings because stubs are now in the text section instead of the no instr section, and Peter Zilstra gets cranky with us. So we don't want that. So I'm taking the easy fix, and I have to go through all the code. That's actually what I'm doing after the conference. Before I get to the class, I have to do this. So I have to go through all the code and figure out where the stubs that are supposed to be no instr are no instr, and I got to go make sure kernel developers get those accepted, and then we won't get that happening. The hard one, LLD, this is part of LLVM, unexpectedly removes definitions of weak symbols. So when you turn on Fortify, this is, we use function shadowing. When you turn on Fortify, it adds weak symbols to the object file, and everything doesn't calculate correctly, and then sometimes you can just jump off into oblivion and the kernel hangs. And we believe that's an LLD problem. So there's a bug that's been submitted to LLVM. It has not moved. So if anybody wants to do a really nice, interesting, juicy bug that would really help out a lot, it'd be really cool if someone were to take a look at this one. If you know LLVM, I imagine it might be easy, but I know I looked at that. It's going to be a wall for me. So I hope somebody can jump at that. Overall, 18 LLVM issues were reported. 5 have been fixed. 2 have pending fixes. And I think the LLD problem is one of those. So actually using them is really, really straightforward. Just apply the patches, do the configuration thing, build your kernel, boot it and do stuff, and then the results, they're stored in sysfs. It's the file called profraw. And then you just run your post-processing stuff, just like any other code coverage. The prof data is specific to the version of LLVM, and then you can merge it, and then you can do all the reporting later on. So you do need a version of LLVM to manage the prof data that was used to compile. There's some fidelity there. And then human-readable output gets generated. I might be able to show some of that. So here's what the coverage report looks like. This is the HTML version. It'll generate JSON and all that if you want it. Function, line, branch, and MCDC. Obviously, you see not as much for MCDC. This is what it looks like when you click through one of those links. This is, I looked hard and I finally found some place with 100% unique cause MCDC coverage. So here's an example. inat.c is being fully exercised when you turn on, that's too bad Shua's not here, the k-self-test code and the k-unit test code. And then during Shua's presentation, I reported some of this to let her know for this kernel 669 with def config turned on, Wentao ran 30 times, it must have taken forever to do this, for each different type, and found that we got up to 25% coverage using LLVM, line coverage, statement coverage, and then MCDC was about 7% using this. So we're there, but it's gonna be an uphill climb to get as much coverage as we want. That's just using k-self-test or k-unit boot, syscalls. So there's some weirdness. It's a kernel. There's always some weirdness. right? No two kernel measurements are ever going to be the same. You get timing, interrupt activity, cache state, et cetera, et cetera. Fortunately, the regulator, C178, doesn't require precise test to code mapping. So I don't have to run this thing and always get the same result. Great, but minimizing non-determinism is going to improve outcome consistency. We want to do that. So a reset mechanism was added to the patches. You can echo 1 to one of the files in the sys interface, and it'll empty out the counters so you can start again. But it doesn't ensure consistent internal state. So you will get slightly varying results every time you run this. There are additional mechanisms that we have identified for follow-on work. There's an easy one with the deny list, which will prevent, you'd have to patch that in yourself, but populate kernel code with no inster. And then I'm speculating on a allow list approach. This would require cooperation in multiple levels. I think probably a command line argument and LLVM and attribute. So that's gonna be pretty complex. And there's other things like runtime, temporary disablement, those things, so that you can set up a test, run it, set up, turn it on, run it, and turn it off so you don't get the setup and tear down in your results. So those are things that we are looking at. And this I wanted to propose to the crowd because I think this might solve one of the boot time measurement problems we have. What I think we can do is add a 64-bit field to store the current monotonic tick value. So as it's instrumenting code, one of the things would be to update in the instrumentation section the current tick value. Now, for hot pass, it's wasted. It's a waste, right? Because it's going to be overwritten too many times. But for initialization code that only runs once, hopefully, enough of it runs once, you probably would get an accurate idea of when your initialization was entered and exit. And because this is really low overhead, it's coverage isn't zero overhead, but it's very low overhead, especially compared to print Ks and ftraces and all that kind of stuff. So you might actually be able to justifiably say, I could probably get pretty close to micro, if not nanosecond granularity for startup. So I don't know if this is a good idea. I'm sure a lot of people are going to rebel at putting 8 bytes of additional information. But I think it would be a way of getting really tightly granular data for especially initialization and boot time stuff. So that was probably a lot. I can do questions. We got plenty of time for questions. Cool. So tell me this is terrible. Any questions you have, whatever. Floor's open.
Okay, so by monotonic tick value, I assume you mean a cycle counter?
Something like that. I think the CPU has, right? It just
CPU has a cycle counter.
Right,
Well, most of them. Right. Most of the ones that are in use.
Right.
So how often? I'm wrapping my head around what G code or what the coverage code. Sure. What does it store, and how often does it store it? I mean, how much data are you talking about?
It stores it in sections in your object file, separate sections. Just like G code stores it in sections, just like LLVM does.
Oh, okay, I will make one comment on what you said there about it being a benefit to store it in a different thing. It's not a cache benefit to store it in a different section. Right, so you're going to get a bunch of cache misses.
That's fair. Yeah, that's fair. It still has to find it and store it, right? Yeah.
Okay.
Yeah.
Otherwise, let me know when it's upstream. I'll give it a whirl.
I mean, I'm hoping somebody will say, well, that won't work for this reason, but if not, then.
Well, I don't know.
I don't know. All right, maybe it'll make it out of this room.
When I can play with, I can play with it now, right? I can go with the patches, but I'll wait a little while.
You won't get the timer tick value, but today you can play with the patches.
Right. Well, there's some other work that's got to be done to unify the cycle count handling. So anyway. I'd
love to hear ideas or any other comments on this as well. Thank you.
Have you looked into error injection functionalities in the kernel?
There's tons of facilities for it, yes.
Does that help?
Unreachable code is where error injection would be useful. And I forget there's a 5 magic or 3 or 4 magic, maybe somebody knows off the top of your head. There's like inspection, all that, so that we use whenever we have unreachable code, we have ways of either error injection to hit it, or there's like you can sit with somebody, explain how it works, those kinds of things. So that solves the unreachable code problem. But otherwise, coverage, just coverage. Yeah.
We're actually doing that in kernel CI right now, like enabling tests that are actually injecting errors And the counterpart of it is the code coverage, which right now in kernel CI, what we're doing is gcov. It's still going upstream in kernel CI, it's not like a fully production. But the idea is to match both things, right?
I'd love to get you to do LLVM code coverage. I think you're going to get a better result.
Yeah, for sure. I believe in that.
Yeah. Yeah. I put my code in there, so prove me wrong, but it doesn't give good results. Yeah.
Okay, so did you run, I would be really interested to see the difference in code coverage between LTP and K-self-test. So I mean, you got 21% for one and 25% for the other. What happens if you do them both? Are they overlapping a lot in coverage because they're like doing syscalls, or I mean,
well,
or could you beef it up to like 30% or 33% or something
let's see.
if you did them both?
Actually, I just did a build and I turned everything on, right? But what you're looking at here in this presentation is Wental went to the trouble of like adding all that up. I think he wrote a Python script to add all that up. I haven't done that, right? So this is running with everything turned on. So I can't tell you how much it is. But this is like I turned everything on. This is def config with some other stuff and everything. So like this is running right now. I think the best MCDC I got was 3% here, 21% here. So this is the 6.12.1 kernel that you're looking at right here on this one. So yeah, so I think he was using the averages maybe, but yeah.
Okay.
Yeah.
Oh, well, yeah, the question is just, is K-self testing different stuff than LTP? That's kind of my question.
Right, test them in isolation too, right?
Yeah.
Yeah, I'd like to do that, and Shua wanted us to do that too, so that we can show a graph of improving coverage too. I really would like to do that. That'd be great for CI. Yeah, yeah.
You know, it could be interesting after you run like LTP and K-self test and all of that, start running sysfuzzer and see which of the new tests it generates increases your coverage. And then you kind of know, okay, that's a gap. Maybe we should save it as a test.
That is part of the verification cycle, exactly. That's precisely it. Yes. Whenever you have a gap, you're not testing well enough.
Right,
Yes.
and then you might as well just take the test it generated and put it into K-self test, right?
Yep.
Same
Whatever.
thing.
Yeah, exactly. I agree. Yeah. And that's what we need to do. We need to close all those gaps. It tells us where to go look. Yeah. Of course, that's got to be driven by requirements too. So that's a whole nother story. Yeah.
It's one of the things not blocked by requirements, though, just increasing
Correct.
the test coverage, right? After
Correct.
that, we could say, okay, great, we already have all of this. So.
Just like your work with kernel API stuff, right? There is tons of low-hanging fruit. Please pick it off the vine. We need that testing.
Curious, what architectures are you interested in, or are you interested in general coverage of the kernel, regardless of the architecture?
I can't speak of Boeing interest in certain architectures. I can't speak on that. But like as a general, without a hat on, right? Like we all know, ARM, Intel, and RISC-V, right? Those are the major players right now. This works for all of that because it's actually a really simple design. Yeah.
Okay, can you use this for minimizing the Linux kernel, for finding dead code, or obviously have to have a comprehensive workload?
Yes, that's exactly right. You have to do enough of a workload to know what you're hitting. But yes, it can be. It is, well, so Boeing is opening up its minimal kernel project. And so that is actually something that's going to be done out in the open. Yeah.
Are you guys, okay, that's a whole separate thing. I'll
No,
talk
please,
to you
yeah.
about that.
But
Well,
yes,
so
coverage is part of that.
Are you doing a minimal kernel project in like Yocto or?
Alyssa is, I think it's going to be done under the auspices of Alyssa,
Okay.
of the Aerospace Working Group.
Probably Yocto?
Oh, yeah, absolutely.
Okay.
It's Yocto. Yeah, no question about that. Yeah.
Okay,
Yeah.
great. I look forward to
yeah.
loading a meta layer
Yeah.
sometime.
Coverage is a necessary part of that. You have to know what you're hitting and what you're not.
Right.
Yeah. Cool. Anything else? Thank you, everybody.
Okay, thanks.